Welcome again to the second experiment of Electronics and Microcontroller Lab EE235. This is Ahmed Fawzi and I'll be explaining the importance of electric circuits today. The electric circuits theory provides an important foundation for learning as a practicing engineer. You are an engineer, you must know what electric circuits is and to integrate it with mechanical engineering. The electric circuits play an important role in many electric and mechatronics engineering applications such as satellite communication, computers, telephones, televisions, medical equipment, and power lines. As you see, there are different applications and uses for electric circuits. And as we have seen in the last video, there are different circuits elements like LDR, which is type of sensors, light detector resistance. We have ICs, microcontrollers, microprocessors, batteries, Arduino, transistors, LEDs, diodes, capacitors, inductor, resistance. And we are going to deal with the majority of these components in this course. To form an electric circuit, we must have a battery, which is electromotive force. We must have resistance or the load, and we must have a conducting wires. Now we are going to explore some definitions. First, current. Electric current is the time rate of change of charge, and it is measured in amperes. The unit of current is ampere, and ampere is 1 coulomb per second. Second, we are going to explore voltage, which you may consider as a pump. If we have a turbine here and we have water flow, so the turbine pushes water in order to... The same concept apply for electric circuit. If we have a pump, which is a battery, and it pushes current inside the conducting wires. We have two types of current. We have direct current, DC, and we have alternating current, AC. For the DC, the current remains constant with time. As you may see here, the current is constant with time. On the other hand, we have the alternating current, which varies with time, like here we have sinusoidal signal. The uses of DC in batteries and some special generators, and the AC uses in household to run the air conditioners, refrigerators, washing machines, and other appliances. This symbol for AC voltage source, and this one is for DC voltage source, and it is used mainly for a battery. In this slide we have two different connection types. We have series. If you put the first battery next to the second battery, it is called series connection, and if you put them like this connection is called parallel. The main characteristic of the series connection is the voltage will be increased while the current will be the same. While here in the parallel connection, the current increases but the voltage remains the same. So if we have batteries 1.5 volt and 0.5 ampere and we need 3 volts, so we have to connect them in series. But if we need 1 ampere, we have to connect them in parallel. We have here mixed connections. We have these two batteries are connected in parallel. These two are connected in parallel, but both are connected together in series connection. So if we have each battery is 1.5 volt and 0.5 ampere, what will be the resultant volt and resultant current? One of the main devices that we are going to use is multimeter, and it is used to measure voltage, current, resistance, and other things. For example, for this digital multimeter, if we are going to measure voltage or resistance, we have to connect the red probe in this place, which has V or ohm, and we have to connect the black probe to the common, which is considered as a ground. But if we are going to measure the current, we have to replace this red blob from this connection and put it here or there. If we are going to measure in milliampere, so we will put it here. If we have more than milliampere, like up to 10 amperes, so we are going to put it here. If we are going to measure the voltage around this lid, so we are going to put the probes in parallel. If we are going to measure here the current, so we are going to disconnect the circuit and make the connection in series. If we are going to measure the resistance, we have to disconnect the circuit and get the resistance and put the probes in parallel and select the ohmmeter. This is another example of how to disconnect the circuit and measure the current. First, we have to change the probes and put it on ampere measurement. Also, we have to select ampere here. And after that, we are going to disconnect the circuit and connect the probes in series in the circuit. One of the most interesting things that we are going to deal with is breadboard. Breadboard is something like this, and we are going to use in connecting the circuits or different components to each other. For example, if we have these circuits, so we are going to implement them using breadboard and connect them to different components like Arduino or both a battery. The history of the breadboard, if we have a schematic diagram like this and we want to connect these components together as seen in this figure, they used in the past to get a plate of wood and connect the circuit. In this configuration, we have here nails, we have the electronic components, and we have conducting wires, and it was very difficult and very tricky to connect this circuit. So they implement the breadboard for us. So if we remove the top plastic cover, we will see here copper connectors. Here we have different copper connections. We have here first line, second line, third line, and so on. Also, we have here one long copper connection and here another long copper connection. So we may benefit from these in connecting the circuits. So as you see here, we have here 5 pins or 5 small holes, first, second, third, fourth, and fifth. These 5s are connected together as they have or share same conductor. Same applies for the second line and third line and so on. But here, the first line and second line are not connected together. Second and third are not connected, but each of these 5s are connected together. Same applies here for the lead color. All this line is connected together. For the second blue line, all this line are connected together. This is another image for clear illustration. Here we have 5 holes. These 5s are connected together. The second 5 are connected together, but the first 5 and the second 5 are not connected together. Also here for the red and black wires here, we may connect through these pins, and we may utilize these lines for power connections. For example, if we have a battery, so you may connect all the positive to this line and all the ground or the negative to the black line. This is an example of connections. If we have 2 wires here, one is red and the other one is blue, and we connect them as in this or as in this figure. So here they are connected on the same line, same 5, so they are connected. Here also they are connected on the same 5, so this is connected. In the third figure, they are not connected because the blue one is connected on D, which share 5 connections, and the red one is connected to E, which is on another line. In the fourth figure, they are also not connected because these 5 are not connected to that 5. If we have schematic diagram like this and we are going to connect them in series, we have 3 resistors. So we may connect them in the breadboard as following. First, we are going to put the first resistance in series to the first resistance. We are going to put the second resistance. After that, we are going to put the third resistance. And you may notice right now the second leg of the first resistance is connected with the first leg of the second resistance. The second leg of the second resistance is connected to the first leg of the third resistance, and the circuit is closed as follows. We have the positive terminal is connected to the first resistance, and the negative is connected to the other resistance. So it is closed circuit and they are connected in series. Here is a schematic diagram of connection in parallel. So we are going to put the three resistance like this, and we are going to connect the three legs of the three resistors together and the other leg of the three resistors together. And after that, we are going to put the positive terminal of the battery this side and the other terminal to other side. This is another example. Here we have connection in series. First resistance is connected in series with the second resistance. Here we have also series connection but with three resistance. On the other hand, we have here two resistors are connected in parallel, and here are three resistors are connected in parallel. And you may notice that these 5 pins are connected together. These 5 pins are connected together. In the first lab, you may have noticed that the voltage across an element may be positive or negative according to which place that we are going to measure from. If we are going to measure from A to B, so this is VAB and it is positive, and on the same line and on the same time it is negative if we measure the voltage across B to A. So the same value but with different sign. The different sign indicates that the reference direction or voltage polarity. Also, we have an important law which is called Ohm's law. It indicates that the voltage across a resistor is directly proportional to the current I flowing through a resistor. So V equal IR, and you may get these from the same equation. This is a good illustration. If we have here current tries to move inside a conducting wire, the voltage which is a pump tries to push the current to move inside the conducting wire, while here the resistance is trying to resist the current from moving inside the conducting wire. In this slide, we have the analogy between mechanical system and electric systems. Here we have pump, and the pump pushes water inside the pipe. We have here throttle or a valve, and the water is flowing through this pipe. Same applies for electric circuits. We have supply voltage, which is a battery. We have here resistance, which is analog to the throttle here. We have current, which is moving through the conducting wire, which is a pipe in mechanical system. And we have here a LED, which is the load, and it is turned on or off based on the circuit is connected or not connected. The resistance R of an element denotes that its ability to resist the flow of electric current, and it is measured in ohm. R equal V over I from the Ohm's law. And if we draw the Ohm's law figure, we notice that there is a direct proportional between volt and current. If we increase current, the volt will increase, and the slope here equal to the resistance. The power in a resistor is the multiplication of current with voltage, or I square R, or V square over R. Here we have fixed resistors and variable resistors, and we are going to use them in this lab or the upcoming labs. If you are going to measure the resistance, there is a table. You could follow the color code, or you may use multimeter to measure the value of the resistance. For example, if you don't have the multimeter device and you need to use this color code, for example, here we have 6 bands, 6 colors. First color is the first band or first digits, which is red. So the red one is 2, so we will write here 2. The second digit here is 7, so we will write here 7. In the third digit it is yellow, and we have here number 4. After that we have black. Black is a multiplier, which here we will multiply by 10 to the power 0. So we will put it here, and this value will become the resistance, which is 274 ohm. And this band indicates the tolerance. It is red, so the tolerance here we have plus or minus 2%. If we have another types of resistors, here we have 6 bands, 6 colors. We may have 4 bands or 5 bands. For example, 4 bands, we have here brown. Brown is 1. After that we have red. Red is 2, so we will put 2. After that, the third color is the multiplier. We have here green, which is 5, so we will multiply by 10 to the power 5. So the value of the resistor is 1200 kilo ohm. The tolerance here is plus minus 5%, as we may see here in the tolerance column. There is a definition called a short circuit. A short circuit is a circuit element with a resistance approaching to 0. For a conducting wire, same wire, we have here short circuit. An open circuit is a circuit element with resistance approaching to infinity, which means that I have a disconnection here in the conducting wire. This is an example of Ohm's law. In the circuit law, we are going to calculate the current and power. Here we have a battery, 30 volt, we have resistance 5 kilo ohm, and we have current here. So it is very simple using Ohm's law, I equal V over R. So we have here voltage is 30 and R is 5000. So the resultant current will be 6 milliampere. For the power, I multiplied by V, so 6 milliampere multiplied by 30 volt, so it will give us 180 milliwatt. For the first experiment, you are going to implement it and measure the values. After that, you are going to calculate the percentage error. Note that the percentage error is experimental value minus theoretical value divided by the theoretical value, and after that you have to multiply it by 100. For the second part of the experiment, we are going to explore different concepts like nodes, branches, and loops. For these circuits, they are equivalent to each other. So if you focus, you will find that this current source is connected in parallel to this resistance and in parallel also to this resistance. So if you see, this current source is connected in parallel to these two resistors. And after that we have 5 ampere. Here we have a voltage source. So for example, we have here first node, second node, third node, and they are the same. So we may make them one node and identify them as B. Here we have another node. For these 4 nodes, they are the same, so we may name them as C. For element connection, 2 or more elements are in series if they are exclusively share a single node and consequently carry the same current. Here we have 3 resistors connected in series. We have here single nodes. Here we have single nodes, so they are connected in series, as you may see here. In this animation, they are sharing same current passes through R1 and R2. The other concept here, two or more elements are in parallel if they are connected to the same two nodes and consequently have the same voltage across them. For example, here these three resistors have three wires and they are sharing same node from one side and the same node from the other side, so they are connected in parallel, which means that the voltage across the three resistance or the three bulbs here are the same. If this battery has 5 volts, so 5 volt will be applied to the first, second and third bulbs. In this animation, it means that the voltage across R1 and R2 are the same as V source, but here the I are divided into two branches here. I will divide it to I1 and I2, and they are connected together after they finished the parallel connection and return back to the circuit. Here is an example about series parallel connections. I want you to identify the series parallel connection in these circuits. First, you may pause the video and tell me what is series and what is parallel. For the first circuit here, we have R2 and R3 are connected in series. So we are going to add them, R2 plus R3. And these two are connected in parallel to R1. So R1 in parallel to R2 and R3 together. So here R1 is parallel to the equivalent of these two resistors. In the second figure, we have here R1 is in parallel with R2, so R1 parallel to R2, and they are in series with R3 plus R3. In the third figure, we have R1 and R2 are connected in parallel. So you may notice that the first terminal of the second and first resistors are connected to the same node, and here, on the other hand, we have the same node which is connected, and on the other hand, we have the second terminal of the R1 and R2 are connected to the same node. We are moving now to Kirchhoff law, which is an important law in electric circuits. The IV relation for a device tells us how current and voltage are related within that device, which is Ohm's law, while Kirchhoff laws tell us how voltage relate to other voltage in a circuit, and also how currents relate to other currents in a circuit. So here we have KCL, which is Kirchhoff current law, and we have Kirchhoff voltage law. For the Kirchhoff current law, KCL states that the algebraic sum of current entering or leaving a node is zero. So if we have here 5 currents, I1 is entering, I2 is leaving, I3 is entering, I4 is entering, I5 is leaving. So we may write this equation: I1 minus I2 plus I3 plus I4 minus I5 equals 0, which is KCL. So if you are rearranging the above equation to make all the entering currents on one side and the leaving currents on the other sides, so we have here 2 and 5 are leaving, while 1, 3 and 4 are entering. So the equation will become as follows. Another form of KCL, the sum of all currents entering a node is equal to the sum of all the currents leaving the node. Whatever goes must come out. As an application of KCL, combining current source in parallel, for example, if we have here I1, I2 and I3, Here we have I total, which is leaving, and I2 is leaving. On the other hand, we have I1 and I3 are entering, so the equation will become as follows. So I rearranging the equation will make I total equal to I1 minus I2 plus I3. So we may replace these current sources by one equivalent current source which has this equation. Now we are going to explore Kirchhoff voltage law KVL, which states that the algebraic sum of all voltage around a closed path or loop equal to 0. Consider the circuit. For example, if we are going to start from here, so we have here minus V1 plus V2 plus V3 minus V4 plus V5 equal to 0. So if we are rearranging the previous equation, we will have here V2 plus V3 plus V5 equal to V1 plus V4. So another form of KVL, the sum of voltage drop equal to the sum of voltage rise. Also, you may note that KVL can be applied in two ways, by taking either a clockwise or counterclockwise step around the loop. So I have moved like this, which is clockwise. If you would like to move in counterclockwise, so that's fine also, and it will give the same result. Now we are going to explore another concept, which is voltage and current division. Here we have, first we have series resistors and voltage division. Recall that series means two elements connect at the same node. Series connected circuit elements carry the same current, as you see here in the animation. From the shown figure, we are going to make KVL at the loop. So minus Vs plus Is, which we are going to make KVL here at this loop. Please note that I source are the same for all these components. So we have here minus Vs plus R1Is plus R2Is plus R3Is plus R4Is R5Rs plus R6Rs plus R7Rs, and all of this equal to 0. You may get Is as a common factor, and you have here all the summation of the resistors on the circuit. So we may replace all 7 resistors by an equivalent resistors and call it R equivalent, and R equivalent equal to summation from R1 to R7. So V source equal to I source multiplied by R equivalent. The equivalent resistance of any number of resistors connected in a series is the sum of the individual resistance. So here we have 7 resistors, and they may be replaced by an equivalent resistors, which is the summation of all these resistors. So the voltage divider rule. Here we have Vs equal I multiplied by summation of R1 plus R2. So I equal Vs over R1 plus R2. So this is very easy and very typical, like Ohm's law. Now we are going to explore the voltage across R1. V1 equal I multiplied by R1. I1, we have agreed that I here is shared along the circuit. So I multiplied by R1, put I, which is Vs over R1 plus R2, and which is this thing, and we have to multiply it by R1, so we are ending up with this equation. Same applies for V2, which is equal I multiplied by R2, so the same equation, but we are going to put here R2. So generally, Vn equal Rn multiplied by Vs over the summation of R. For example, if we are going to measure V out here, so we are going to multiply Vs by R2 over R1 plus R2. Same here, if we are going to get V2 equal Vs multiplied by R2 over R1 plus R2. Example, determine the voltage V in the shown circuit. So we are going to use voltage divider. V1 equal V source, which is 12 multiplied by 16 over 16 plus 8, which is equal to 8 volt. Same for V3, we have here 12 multiplied by 4 over 4 plus 8, which is equal to 4 volt. Now we are going to make KVL on the shown loop, this loop. So we have here minus V1 plus V3 minus V equals 0. So if we solve this equation and put V1 8 and V3 as 4, we will get V as minus 4 volt. The second concept, which is called parallel resistors and current division. Recall that parallel means elements share the same two nodes and therefore have the same voltage across them. Also, I here are divided to I1 or I2, I3, and they are connected together after passing the parallel connection. The circuit shows two resistors connected in parallel, R1 and R2. So we may have V equal I1 R1 equal I2 R2. As you may notice that I here is divided to I1 and I2. So V here equal to I1 multiplied by R1 or I2 multiplied by R2. Rearranging this equation will give us I1 equal V over R1 and I2 equal V over R2. If we are going to get total I equal I1 plus I2, which is equal to this, and if you get V as common factor, so you are ending with up V multiplied by 1 over R equivalent, which because of these connections are in parallel. 1 over R equivalent equal 1 over R1 plus 1 over R2 and so on. And we have a special case here. If we have two resistors connected in parallel, it means that R1 multiplied by R2 over R1 plus R2 equals to the R equivalent. So generally, a circuit with k resistors in parallel have the equivalent resistance as follows. 1 over R equivalent equals summation of 1 over R1 plus 1 over R2 and so on. And from here, the current divider rule is common. V equal I1 R1 equal I2 R2. So as we have agreed that R1 and R2 are connected in parallel, so this is R equivalent multiplied by IS. So I1 equal to R2 over R1 plus R2 multiplied by IS, and same here for I2. So for example, if I am going to get I1, so it means that IS multiplied by I2 over R1 by R2. And if you need to get I2, it means that IS multiplied by R1 over R1 plus R2. So here you are getting the opposite. Example, find IS, I1 and I2 in the shown circuit. We are going to reduce the circuit. First, we have 3 ohm and 6 ohm are connected in series, and their R equivalent equal to 6 plus 3 equals to 9. So the circuit becomes as follows. After that, we have here 18 and 9 connected in parallel. So 1 over R equivalent equal 1 over 9 plus 1 over 18. So R equivalent becomes 6. and the circuit becomes as follows. So from Ohm's law, I is equal volt over resistance. So we have here volt equal 120, and we have here the resistance or 6 plus 4, and I is equal to 12 ampere. Now we are going to calculate Vxy, which is the voltage across these points, which is equal to Is multiplied by the resistance, V equal IR. Is, we have got it from the last line, 12 multiplied by the resistance equals 6. So the result equals 72 volt. After that, we are going in the backward direction. I1, which is here, equal to V across XY, V XY over the resistance here, which will give us I1. And I2 is the same, Vxy over 9, and it is 8 ampere. Another example, find the current in the 6 ohm resistor in the shown circuit. Solution here, we have 4 and 6 are connected in parallel, and they are connected in series with 1.6 ohm. So the resultant or the equivalent equal to 4 ohm. We are ending up with this circuit using the current divider. I node, which is here, is equal to 10 multiplied by 16 over 16 plus 4, which is equal to 8 ampere. Another current divider, so in order to get I over the 6 ohm resistor, so we are going to multiply IO, which is 8, multiplied by 4 over 4 plus 6, which gives us 3.2 ampere. That was for today's lab, and I have a good news for you. All the derivations is for exploration and for your knowledge, so it is not required from you, and the examples that I have shown you is for clarification. You are going to implement these circuits or similar circuits in the lab, so you are going to measure them experimentally, not analytically. But if you would like to get benefit from the analytical solution, you may verify your answer. If you made the circuit experimentally and you would like to verify whether your answer is correct or not, you may use one of the methods that we have explained in this video, like KVL, KCL, voltage divider, and current divider, and you may use, of course, Ohm's law. That was for today. Thank you so much for your listening, and I hope you enjoy your lab. In the end, I would like to thank Dr. Walid Isa and Dr. Lubna Saeed. So I have benefited from their slides and their explanation to prepare these slides. So thanks for them, and thanks for your listening, and see you inshallah next lab.